All right, let's look at the octahedral structures and the polarity of those. And again, we're going to imagine that everything on the outside is like a fluorine that's pulling electron density to it. It could be something else that's pushing electron density, but the same arguments apply. So let's start off with our base geometry. We have an octahedral structure where everything on the outside is exactly the same molecule or the same atom, and I'm going to pick fluorine. Now, if we have a fluorine on top and a fluorine on bottom, the pull for electrons by the fluorine on top is going to cancel the pull for electrons by the fluorine on the bottom. Those dipole moments cancel out. The fluorine to the back is going to cancel out with the fluorine to the right. The fluorine on the right is going to cancel with the fluorine on the left. Overall, it's completely symmetric. If you have that kind of symmetry where everything is going to cancel each other out, there is no winner, and it is a non-polar molecule. Now, let's start adding some lone pairs. If I add one lone pair, it's always going to be polar with one lone pair. There's nothing to cancel or balance out that lone pair, but let's take a look anyway. I'm going to go ahead and ghost out the one on the top to make a square pyramid structure. Now, the pull to the back is going to cancel out with a pull to the front if those are fluorine. The pull to the right, let's say that's fluorine, is going to cancel out with the pull to the left. Okay, no winners yet, but there's nothing to cancel out this pull towards the bottom. So, since this is not symmetrical, there will be a winner. The electrons will be pulled towards one side, and we're going to call that a polar molecule overall. Let's add a second lone pair. So if I put my first lone pair on the top, it's important to know where the second lone pair goes. The second lone pair is going to go on the bottom, as far away from the top one as it can. That leaves us with a square that's flat, a square planar molecule. Well, let's go ahead and look at the polarity of this molecule. The top electron pair is going to counterbalance the bottom lone pair. That's symmetrical. Any pull towards the back, if those are the same atoms, will be canceled out with a pull to the front. Okay, no winner there. A pull to the right is going to cancel out a pull to the left. There's no winner overall. This is a completely symmetric molecule, and because of this, this is non-polar. All right, let's go for the next variety. 3 lone pairs. If I put my first lone pair on top, I'm going to put my second lone pair on the bottom. Then my third lone pair has to go in the middle. It's not symmetrical. If it's not symmetrical, there will be a pull for electrons towards one side. It will be polar. Let's double check. The pull to the right is going to cancel out the pull to the left. Great, no winner, but there's nothing to counteract this forward pull if that was a fluorine. So there will be a pull. It is polar. Let's add one more lone pair. Top lone pair balanced by bottom lone pair. If I put my third lone pair on the back, I'm going to put the fourth one on the front. This is a symmetric molecule. Top lone pair and bottom lone pair cancel out. Front and back lone pair cancel out. And if these were, let's say, 2 fluorine atoms, the pull to the right is going to counterbalance the pull to the left. There will be no pull. This is a non-polar molecule overall. So go ahead, keep looking for symmetry in these. If you've got something that's not symmetric, like this square pyramid molecule, well, then there's no symmetry. There will be a pull for electrons. There must be an invisible lone pair down here. Without the symmetry, there is a pull, and this is polar. If you join me in the videos below, I'm going to go ahead and go over some straightforward molecules. How do you go about looking at a formula and telling polarity? But I hope this helps.